finite energy solutions to the Euler-Lagrange equation. And we saw there was a dimensionality dependent. First thing, we started at d equal to 1. So, this is spatial dimensions. Okay. So, in d equal to 1 we saw King soliton, and once we went to d equal to 2, this was the barrier due to Derrick's theorem, and we saw that if you added gauge fields in the story we could get vortices. Okay. And just to remind you, what we were looking at was pi 1 maps from the, so the boundary conditions were really at this thing, and at some, and there was some group symmetry G broken to some H, and so the example we considered was really trivial. We had U1 and that is an S1, and we got vortices which were quantized and that were carrying flux, magnetic flux. The more general thing would be something like this, and then we moved on to 3 dimensions, and you would get, we saw that we got monopole solutions. We got monopoles, and now the spatial boundary is a 2 sphere. So, you would be looking from the S2, which is at infinity, to again you have some symmetry G broken down to this, everything locally gauged, etc., those details, but I am just writing sort of the kind of things you would look at, and it is obvious that this list should continue, and except one may say, look, we live in 3+1 dimensions, there is no need for us to go beyond that, but just for the heck of it, let us just look at what you would get at d equal to 4. Then things should be classified by the boundary at infinity would be a 3 sphere. So, you should start looking at pi 3 of whatever G mod H or whatever, something like this should be classifying these things, and what should you call these objects, etc. Okay. We will see that these objects they have a name, they are called instantons, Euclidean instantons. Okay. There is one way to get to 4 dimensions staying in 3+1 by Wick rotating time. Okay. So, one trick of going to is to Wick rotate time. So, you take t goes to I tau. Okay. So, in fact, you can see that if you were so you can even go back to all these various solutions and look at it. So, what the idea here is, it takes one from d+1 dimensions to now I should not write it this way. So, a space time of signature say 1 comma d to Euclidean d+1 dimensional space. This is what it does. Okay. So, so an example of that would be to take d equal to 3 and you would get something analogous to this, but it is clear that you could go and view view these solutions as coming from something like that. So here we started out with a 3-dimensional space, but a solution that we get here we could do some tinkering with it, some Wick rotation or whatever, and maybe we can get a solution. So we could also go the opposite way. We could take some direction or something and Wick rotate it and make it look like this. Okay. So you may, but now these solutions won't be time independent anymore. They will pick up a particular time dependence which is dictated by whatever coordinate you are going to Wick rotate. So you can go both ways. Okay. So what we will do is to look at something like the king soliton, because it is the smallest dimension and we can draw nice pictures, and try to understand, is there any phenomenon which could be captured by this thing. Okay. So here what I am saying here is, consider the case which is 1, 0 dimensional, and what would such a system be? That will be a quantum mechanical system, it is not a field theory. Okay. So if you did this and started out, so in other words you can map, so the reverse procedure that is reverse of what I am saying out here can take, see what is happening here is that there is time in this, but what we have done is made everything time independent, and we were working with the energy density or working with the Hamiltonian really. So so the thing is, you could do the opposite and see if you get the Lagrangian or whatever. Okay. So let us see how that works. So reverse procedure can take one from one spatial dimension from a d equal to 1 solution, king solution, to something in quantum mechanics. Okay. So let us look at, let us draw the picture of the king soliton and act as if that were time, the x dimension as time. Let us just act as if that is correct and see what you get. Okay. So if you remember the king soliton in our example, we did the 5/4 thing, there were two. So the potential was very simple, it was something like this, double well plus a minus a phi versus x. This was the potential, and so we drew, so this was the solution, sorry, u of phi versus phi. Okay. And this is phi of x versus x, and so if you consider the kink, it interpolated from something which went from this thing is phi minus a and plus a. Okay. So now what I am saying is that let us think of this as time. Suppose this were time, let us see what is this process. Okay. Can someone tell me what would be the process? So let us look at what happens at t equal to, as t tends to minus, around t tending to minus infinity. This yellow color is very bad, so I will not use too much. So as t tends to infinity, you are starting out your system in something in this ground state. Okay. So the state system is such that, so phi becomes now also, we should think of this as just some q of t. Okay. So this is the replacement that we need to do. System is say at minus a, and at t equal to plus infinity, say the system is at plus a. What would you call such a process? Tunneling. Okay. So you can see that a kink, the Wick rotated solution weak rotated solution appears to capture the process of tunneling from one vacua or one vacuum to another. Okay. So, the question is how do we understand something like this. So, I will write just one formula from quantum mechanics and then we will so a formula from QM okay. So, the picture is as follows. What we have in mind is, suppose we have a barrier and you are tunneling through that. So, you have some barrier potential V of x versus x or q, should I call it q maybe, okay. And so, this is, you have some energy E, and so you have classical turning points, okay, which is x1 and x2, and you must have done some scattering problems and worked out what is the tunneling probability. So, the probability, so magnitude of the tunneling probability is goes as exponential okay. So, this is the energy which we are choosing. So, let me just define h cross square kappa square upon 2 m. So, it is just a particle with mass m, and this thing should be equal to V of q minus, so it is kappa is some q, V of q minus E. So, kappa square, kappa will be root 2 m into V minus E divided by h cross. Okay. So, this is just proportional to integral of x1 to x2 dx of dq. I should use q's, right. So, q1 q2 q1 to q2 dq kappa of q, okay, which I want to put back in terms of this because I remember it this way, and this is which is equal to exponential of integral of 1 by h bar q1 by q2 dq So, let us look at this a bit. We know that the classical limit is h bar being small, but look at the h bar dependence of this thing. So, for instance, this formula you can check for the easy one to do is to take the square potentials or rectangular potentials, where you can solve it and do matching and stuff like that, and you can work out this thing. But this formula is not derived that way. This way you can see we will agree with that in the case of such potentials, but this is derived by something called the WKB approximation or saddle point. Okay. And so, the point here is so whenever you have a small parameter, usually you think you can do a computation such that you make a the answer for a classical answer, which is h bar equal to 0, and then you start doing corrections. But look at the behavior of this term, okay. It is not analytic at h bar equal to 0. Hopefully all of you know that this function exponential of 1 by x at x equal to 0 is lousy, it is not analytic. There is no Taylor series expansion because it blows up at that point, okay. And so, that is exactly what is going on out here. So, there is not any perturbative way of computing this thing. So the two methods which normally one uses in quantum mechanics, one of them is WKB, or another way is to show that for instance the way I would show that the true ground state, the easy way to see the true ground state is to choose following things. Choose something which is Gaussian here, centered here, so another Gaussian centered here, and estimate the energy for the correct Hamiltonian, and then take linear combinations, and you can show, at least in certain approximate computations, you can show that the plus combination, the symmetric combination, has much lower energy than any one of these two guys, okay, to show you that the true ground state due to tunneling etc. is this thing, okay. But you could ask, suppose what is the probability of starting with a solution at x equal to minus a and asking how long, that is a perfectly allowed initial configuration, and what would be the configuration, and such that you are in this other vacuum at infinite time, which is the kind of thing which we are talking about here, okay. So what one is trying to say is that you cannot do any simple perturbative computation to get these things, okay. So such things are usually called non-perturbative, okay. So the thing is, now how do we go about so the question would be, is there a way of understanding the same WKB kind of answer in another method, and the answer is yes, you could use path integrals, okay. So the Feynman path integral okay. So Feynman path integral actually gives you, suppose you have at some initial time, so you start out with your system being in Qi, and at time, so usually it is done in the following way, you take it to be at some initial time minus t by 2, it is at say Q initial, and you want to know what is the transition of this thing at, so overlap of this thing with the system at some later time t by 2 and goes to some final QF, and later what you have in mind is you take capital T to infinity. So it is like you start out with this sort of a thing, and this just is given by the path integral, and that is just sum over all paths, which you write something like this, okay. Sum over all paths which start at Qi at this initial time and go to Qf and this thing times e power I times the action divided by h bar. Yeah, this is something which we discussed I think in the very first lecture, okay. So what we will do first is to take this action, and we do the problem with this sort of a thing is this is an oscillating integral, and so one trick is to do a Wick rotation, and then you get a convergent integral and you go backwards, but Feynman does not do that. But let us say that we do a Wick rotation on this. So let us look at this action. So what I would like is to do, choose the Wick rotation, Wick rotate, so that I get something which is e power minus s kind of thing, which is convergent. Wick rotate to get a convergent integral, okay. And so let us look at what is, so what we want is to look at this I integral this thing L dt from, so initial minus t by 2 to plus t by 2 dt of some Lagrangian of q dot and q, okay. So the Wick rotation I have suggested there, we have to check the sign that it works out right. So let us take t and say that is equal to I tau, okay. And and then what else do I do? Yeah, so let us look at q dot is dq by dt, okay. Q dot is dq by dt, and that just becomes minus I times dq by d tau, okay. So we can see that now this will go to, once we make this substitution, let us not worry about the limits, but the key point here is this will become minus d tau times, let us look at this, Lagrangian, which is wherever we saw q dot, I should put minus I q dot, but on the right hand side the dot will imply, maybe I should, can I use dot for it, is it okay? Dot now will represent on this side tau derivative, okay, so that I keep the i's explicit, and nothing happens here. Okay. So, this is what the Wick rotation is doing. Let us follow our nose and see what this implies. So, let us take L if it is half mv square, right. So, m minus u of q okay. So, you can see after we do this thing, this just goes to, after we do this substitution, you can see that just this becomes minus m by 2 okay. I am a bit unhappy because the reason I am unhappy is because now I mean I wanted a convergence, so I need to I think take tau to minus I tau. Which limits? Yeah, okay, I haven't written the limits here, that is what I said, I jumped the limits, but I am more in thinking in terms of having a convergent factor. So, I am just suppose we assume that both u and q are nice these things, then what we can see here is that this gives a minus sign, okay.
That's because previously when you defined the Wick rotation it was from space time to space, but here we are going from time to.
So, no, the thing is I want to put a, I am going to put a minus sign here, so that I get something convergent, okay. So, then I just get this to be plus, but that minus sign will take care of okay. Is this correct? If I Wick rotate, dt goes to this thing, yeah, okay. Which one? This will become plus, that will not change this minus sign, okay. So now what you can see here is that integral of dt L become I integral dt goes to minus integral of, oh okay, so I should be going from here, I should be now tau is, so it's yeah, so that was fine, right. So the earlier thing was to go from space to, it depends, yeah, so this is fine, this is okay. So now tau is something like a Euclidean coordinate, so it's closer to what we have written for an x, okay. So yeah, good. So now, so what we get is a dt, okay, of sorry, d tau of okay. So now you can see that if you try work out the equations of motion for this sort of a guy, this this looks like a normal Lagrangian, except there is one change, the potential is inverted, okay. Okay. So in this Euclidean problem we started out with this guy, but what we see is that the potential is inverted, okay, and but nevertheless we can This is not, I mean, it's not so bad. I mean, the point here is we want to, we are actually at the end of the day, we are interested in this transition probability. We would like to compute something like that. And so, yeah. So let us draw this potential out here. So the potential would start looking something, it's inverted. So this is what you would get. Okay. And if you are looking for a solution which is interpolating, did I get the signs correct? Okay. If it is interpolating between these things, you would look for a solution which does this. Okay. So this solution has a, this kind of solutions have a name. So this is called a Euclidean instanton. Okay. And I should explain to you the origin of the name. So the origin of the name is, first thing is, if you remember, we looked at solid. Yeah, you have a question? Because if I think of this as a Lagrangian for some Euclidean this thing, there's a minus sign out here. It's like a flip. Yeah, in the Euclidean setting, it's minus u of q. If you think of this as t minus. Okay. So yeah, so the name is the on is because it's somewhat similar to soliton. Okay. Except when we looked at solitons, we looked at when we looked at solitons, we looked at the one feature was they had finite energy, and we also noticed that they were localized in space. Okay. But now if you think, just take this guy and go back through that procedure which we did earlier, which is to do this kind of Wick rotation. Okay. So then something which was localized in space will become localized in time also. Okay. So it's at an instant. Okay. It's so it's not just localized in space but also in time. Okay. So an instanton is localized in space time, and if you want to think completely in space time, what you would look at, you will, instead of looking for energy, you will look for action, finite action, which after you Wick rotate will become finite energy in some sense. Okay. So something which I have not proved, but we will see a little later in probably in the next lecture or so, that all the solitons that we wrote can always be converted into instantons in a suitable setting. Okay. So it's so this is the difference between an instanton, spelling is wrong, and this was coined by et Hooft. And I think Polyakov called it pseudo particle, but that hasn't got on for whatever reason, but this is the name which is this thing. So for instance, this gives you the title of a very nice book on solitons by Rajaraman. It's called Solitons and Instantons. Okay, that book is at a slightly higher level than this course, and but I would recommend now that you have done this course, you can go and look at that book, and you will find that lots of it you will understand lots of it. I also discovered a nice book by called Topological Solitons by Manton and Sutcliffe. So this is one book, and there's of course the one I just mentioned, solitons and instantons. Okay. And for the idea of instantons, etc., again, this is something I mention all the time. this for me has been very inspiring is Coleman's Eriche lectures. I have very hardly used these books. I have looked at either the original papers or looked at these things. Okay. So now we have a working definition of what we mean by an instanton. We have to look for localized objects which are localized in both space and time, and sort of give rise to a finite action as opposed to finite energy. So let us see how we would get a formula, something which looks a bit like this. So now I have to decide what I should erase. So now what we have is a nice path integral, an integral. So we need to carry out an integral of this kind, dq e power minus s Euclidean of q of tau. Okay. Yeah, is there any question?
What I am confused about is if the limits do not matter, then why would the minus sign matter? Because we could just flip the limits and get a minus sign for the action.
No, but I didn't write the limits. Okay. So yeah, I mean it well, it will matter. It will. I mean let's yeah, we'll see what for some things it doesn't matter, but I mean the order does matter. I mean, okay. So let us see how we would do this sort of an integral, and this is an infinite dimensional integral, and so what we will do is do something, look at a simple example of say dx say e power, so divided by h bar of course, e power say some minus f of x by some, okay, we will look at something like this. Okay, a function which has something like this, and we would like to evaluate this by the saddle point. Okay. So an example, a nice fun example to do is to consider the gamma function or n factorial. So we can derive, so n factorial is equal to integral dx from, in this case, 0 to infinity x power n e power minus x, is it? Okay. Is it x power n or n plus 1? I never remember this. Is it? It's right? Okay, I just got lucky. So I can make it look like this. Is this okay? Okay. I mean for my purposes n and n plus 1 will not matter. Okay. So it's an example of this sort of an integral. So we can just rewrite this as integral from 0 to infinity d of x goes like e power minus x plus okay, I am just so this would be a case where it is f of x. F of x is this quantity x minus n log x. Okay. So this is a nice integral in the sense that this is an increasing function and this is a decreasing function. So if you plot this thing, it has only one maximum. Okay. So what you would do in evaluating this, so let us call this maximum x naught, the leading, so you want to evaluate this, and you want to evaluate it for some for large n. So the way you do Stirling's formula is to say that let us evaluate this guy at its saddle point, and that is just taken by taking this thing and extremizing it. Okay. So you just take f of x, so you will solve for f prime of x x naught. So we have to solve for this equation. So if you just do that out here, what do we get? We get minus 1 plus n by x should be equal to 0, implies that x naught is n. Okay. And what you can do is to further expand it. I did not want to erase this. Okay. So you just go ahead and expand it about this thing, and because it is truly a extremum, you will see that f of x will be f of x naught plus the first derivative vanishes, and because it is a maximum it will have the correct sign, Now one second, I should be yeah. Yeah, so minimum maximum, so I should just yeah, so it will go the right way is what I am saying. Okay, so what I want is so it has to, whatever happens, f of x is, so actually in this case f of x, and what we have in this thing, there is a minus sign, so it will work out correctly. So what was I saying? Yeah, so this function is like this, okay, but what we will get up there because of the minus sign will be something which will be nice and upwards. So you will get x half of x minus x naught whole square f double prime of x naught plus dot 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 dot. Okay. So first approximation is to say that you just substitute for this guy with f of x naught. Okay. So n factorial, so this is for large n, we would like to evaluate this integral, and you will see that your the limits won't matter, but this thing. Okay, so we will see. Okay, so what is it? Yeah, so let us just evaluate that. So we just go ahead and put x naught, that would be just e power, my x is just n, okay, times. Now the key is that you in principle you should say, yeah, I should do it from 0 to infinity, but this will just give you a Gaussian, it's just a Gaussian integral, which would be e power. So now I will just write something. And now I will change the limits. I will say that for large n this is fairly, it's not you can see that the width keeps reducing. So in quantum mechanics you will see that this h bar will determine the width, and you can see that in the limit when h bar becomes small, you can see that you can make things as sharp as possible. So what one says is the saddle point is becoming better and better. Okay. So in this case similar thing will be played by 1 upon n, you can convince yourself that that is the thing. And so if you just work this out, you can already see that we got the leading term in Stirling's formula, but you can also do this Gaussian integral and you will get this important prefactor. Okay. By the way, what was Stirling's contribution to Stirling's formula? It was only the constant, by the way. It was otherwise the general form which we know was already known. Okay. So this is the kind of things you would do. So we can do the same thing out here. So what would be the leading thing would be just the the contribution to this would be just taking the solution to the equation. So the analog of x naught would be looking for a solution to the Euler-Lagrange equation, okay, and you evaluate the action. The analog of this is just to evaluate the action at the saddle point. Okay. So in other words, but what is the saddle point in this case? It is just our normal trajectory. In this thing, this is nothing but the classical trajectory which interpolates between whatever in this example. Okay. So in condensed matter parlance, one would say that this is the mean field answer, and these are the Gaussian fluctuations. Okay, if you have seen it in condensed matter, this is what you would have done whenever you are doing these things, that oh, we will put in the fluctuations and get this. That is what you mean, do this integral. Okay, it's not as simple as this. So so now you can see that what is the structure, what is S Euclidean. So, the equation of motion would be just d square q m d square q by dt d tau square should be equal to du by dq. Is this correct? Okay. So, just going back to what you can see that if I go backwards and Wick rotate back or whatever, you will see that the signs will, you can see that the sign will work out actually with what you needed. So, this is the equation that you need to, so this is the saddle point. Okay, so you and let q naught of tau be the saddle point solution. Actually, we can do I mean this is a one dimensional system, we can do one integration very easily, and so we could use we could do that, right. So, in some sense you specify the energy or whatever, and then you can do the, so you can go back and substitute for so equivalently, yeah, what am I saying. So, you can see, yeah, I will not say anything more. Okay. So, this is what is going on. Okay. So, now it is very clear. I mean next time I will make things more precise, where I will take our king soliton and we will see how it works or whatever. So, the idea here is that we can do this not just for qm, but even for qft. Okay. What do I mean by that? Here this is, so here we did things in 0 plus 1 dimensional time. We could work with d plus 1 dimensional space time, and all these arguments actually just go through. There is nothing different about the thing. It is just that there would be, in addition to a time d tau integral, there will be, in all these formulae you start putting dd of x. Okay. Thank God I use q, so that it does not get confused with x. Okay. So, what we will do now is to, I will just quickly jump back to 3 plus 1 dimensions to discuss what we actually, our goal is to understand what are called instantons in 4 dimensions or 3 plus 1 dimensions. So, we will look at instantons. So, we will take a case in 3 plus 1 dimensions. Okay. So, now we will not do any Wick rotation or anything, we will stay with 3 plus 1 dimensions, but we will remember what we did from this thing. We will look for finite action configurations. Okay. So, what would be the, what is the, so let us just consider the case of pure Yang-Mills. For some gauge field, for some gauge group G. There is no matter, nothing, we just consider pure Yang-Mills. Okay. So, in that sense it is somewhat different from what we looked at in all the other cases. There were scalar fields going around, okay. But we also saw, when we looked at the monopole, we could think of the phi field as coming from something in a higher dimension, from coming from a gauge field. So, it is not so wild to say that we look for only pure Yang-Mills. The action is just S will be minus 1/4 or whatever integral of d4x times trace in some representation, I do not know, fundamental maybe, of, or just write it straight as f mu nu a Okay. So, this is the kind of action we are looking for, finite this thing. So, what we should do is now is to put some behavior such that so the key thing is we need f to vanish at spatial infinity. Okay, so we need okay. So, so now question is, how do we do this? How can we achieve that? So it should say that as you go to both spatial and time in like infinities, you should your gauge field can go to 0. Okay. So one solution is to say that as one goes to spatial infinity, okay, as one goes to spatial infinity, require a mu a to go to 0. But this is not a gauge invariant statement. So can we replace it with something nicer? If you start out with a gauge field which is 0, if I make a gauge transformation, what does it go to? Huh? It goes to pure gauge. So instead of saying this, we just say that it goes to something like G inverse d mu G, maybe there is some I or whatever. Okay, this is pure gauge. Okay. So this is the kind of boundary condition that we have to impose. This is much weaker than this thing. Okay. And just for the purpose of this thing, just consider, I will keep going back and forth. I started off with Minkowski, but we will stick to Minkowski later. So we will just go to Euclidean thing, so I can think of space time as an S3. Okay. So what you will see is that you will have to, so because so what you so you have configurations at infinity given by maps from S3 of infinity to G, okay, in the Euclidean version, not little g, but the group element. In Euclidean space. Okay. So let us take the case of G equal to SU3, SU2, then the group manifold is S3, it is also an S3. Okay. And we know one thing, we know that pi 3 of S3 is, there is an integer worth of these maps. Okay. So there will be some object which is quantized, and there will be no smooth way of going from one or if suppose you find something which has this integer being 1, it cannot go to a 0 sector. Okay. So what we will find is in the Euclidean theory that this is similar to what we had looked earlier, that there is an integer worth like so, and this charge, this will be like in the case of monopole pi 2 of S2 when we had looked at that, where there we interpreted that as a monopole charge. Here this is just called the instanton number. Okay. So I will finish with a question which is the thing, can we write such configurations which have this instanton number. Okay. And the first solutions for various instanton numbers were given by 't Hooft, and then it has been generalized to by truly high power 4 mathematicians A, D, H and M, and each of them is a big mathematician. They wrote a 1.5 page paper I think in Physics Letters, where they wrote out the most general solution, and that solution, so what we will do, so the 't solution is very much like you write out something, we will do some completing of squares kind of trick, and you saturate some bound and you get some equation, you solve that equation. But this equation was amazing. It is not written in that language, it is written, let us consider some n by m matrix which satisfies this equation, and then the consistency conditions turn out to be the same equations we would have solved, and out of the blue they are able to write it. But today we understand, we have a nice geometrical way of understanding it, but when they wrote it out, I mean, it was just out of the blue. So there is a lot of fun stuff which will come. So I will just stop here for today.